Okay, this lecture is over Module 10 of your curriculum titled LAN Security Concepts. So we'll start out with why should I take this module? I have a couple of reasons listed. One is security is very important in general. And a lot of times in other classes, we spend time talking about securing PCs on the network or maybe servers on the network. But it's equally as important, if not more so, to secure your local area network. So what will we learn in this module? We'll talk about endpoint security, which is those end devices I was talking about, sometimes referred to as user devices. We'll talk about access control. It determines what access you have based on who you are or what group you're in or where you're coming from on the network. We'll talk about security threats at layer 2. We will talk about MAC address table attacks, and we'll talk about LAN attacks that are attempting to compromise your local area networks. So, in the case of endpoint security, there are lots of different attacks. This is nowhere close to an all-inclusive list, but in other classes, you should have talked about denial of service attacks, which are attacks that try to cause a server typically not to function correctly by sending it too much traffic, for example. We also have something called a distributed denial of service, which I suspect you may have covered in other classes. I know I cover it in 111 and in the Security Plus class. That is where you have machines, you compromise machines, and they're called zombies. They're sitting there doing nothing until you decide to start an attack, and then you somehow get a message or an action to the zombies to attack a particular host, for example. So there may be thousands, tens of thousands, hundreds of thousands of machines all of a sudden attacking a host that you want to do the denial of service attack on. Data breach are attacks that try to steal confidential information. And then malware, and a shortening of malicious software. This would be viruses and worms and Trojan horses and a whole slew of attacks, like I said, that you've probably discussed in another class. There are some functions on network devices or network devices themselves that provide security. The first one they have here is a VPN enabled router. So VPN, of course, is virtual private network. The definition I like to give is it is a way to create a secure encrypted tunnel from your end device, for example, your laptop or your desktop somewhere, to a VPN concentrator or a VPN enabled device. In this case, they're talking about a router. So the traffic leaves your PC encrypted, travels across a possibly very public infrastructure, and does not get decrypted until it is at this router, which is presumably on your network somewhere that is secure. The next thing, NGFW, is a next generation firewall. And what they mean by next generation is a quote older firewall would make decisions on source or destination IPs, source or destination ports, that type of thing. A next generation firewall provides something called stateful packet inspection. It is powerful enough in real time to rip apart the packets and inspect what's inside and keep track of conversations or see if any malicious intent is being embedded in the frames that are traversing the firewall. One thing they mention here is they talk about intrusion prevention system. Before we talk about that, I would like to talk about an IDS, which is an intrusion detection system. An intrusion detection system uh, passively watches network traffic. That means it sits on your network and watches the traffic flow across the network and tries to determine if there is malicious things going on. If it is, the detection part of that means that it detects a problem and then it'll send an email, send a page on a monitoring system in a network operations center, change something to red to indicate there is a problem, and then let a human go check and see what's going on. An intrusion protection system does the exact same thing. However, at the end, it will actively put a stop. It'll block a port or take a machine off the network because it knows something's going wrong. So it actually takes action. They talk about an advanced malware protection. Basically, this is also continuous monitoring of network traffic, trying to look for known viruses, known worms, known malicious software, and how they behave, and try to detect that on your network. And then finally, NAC stands for Network Access Control. For example, Cisco Identity Services Engine. What it does is it works to authenticate and determine what access users should have or different groups of users should have. 10.1.3 is talking about endpoint detection. They have a graphic down here that has all kinds of devices shown. So presumably we're at home. We want to be secure, so we're using a VPN. That VPN goes over public infrastructure, for example, the internet with a capital I, and then terminates at a VPN-enabled router. Our traffic would then flow through a next generation firewall. What they're showing here is that we are inspecting traffic that is flowing both ways through the firewall. We have a network access control. It's doing a couple of other things. We have that identity services engine that we talked about before that's doing policy enforcement. And then in the Security Plus curriculum and class, we talk about the 3 A's of security. They are authentication, authorization, and accounting. So basically, authentication is proving you are who you are. Most common way is by providing a user ID and password. Authorization is once you've proven that, for example, I am Wayne, what does Wayne have access to do? And the third A is accounting. Wayne logged in at this date and time. He changed this record in the database. Wayne logged out at this time, etc. So it keeps track so that if we need to go back and audit or try to track down some bad behavior, we can do that. We may have email security appliances or web security appliances. We'll talk about those in a moment. And then down here, a WLC is a wireless LAN controller. This is for managing access points. Someplace like BCTC or the University of Kentucky has many, many, many wireless devices, and this makes sure that the policies and authorization and that type of thing are consistent amongst all the access points. And then down here we have all of our end user devices, which may have advanced malware protection, may have virus protection, spyware detection, etc. So there are a lot of things that a network administrator, especially if they end up being the system administrator of these devices down here, have to understand and be aware of. Go back and talk about Cisco Email Security Appliance. Basically, this is going to work in conjunction with your mail system, and it's going to do things like if it sees an email that has a known threat, it's going to either quarantine or delete or block that email. It's going to try to detect malware, again, that is in email. If there are links to known bad sites, it may just discard that link, or it may discard the entire email. If we have new sites that we think are being malicious, it's going to block access to those, and it's going to try to encrypt outgoing mail so that we don't have data loss. Another thing that we have at the University of Kentucky, I don't know that KCTCS has turned it on yet, but any email that comes from outside UK has a little graphic at the top that says external email message or something to that effect, so that you know it came from somebody outside your organization. The next section talks about web security appliances. This is basically the same thing. It's going to have things pass through it before it goes to the actual web server. Some of the functions that it may have is blacklisted URLs. At UK, if we determine a malicious site and you actually try to go to that in a web browser, it's going to come up and say, hey, this is a known bad site. We've blocked access to it and will not allow you to go there. You have URL filtering, which will decide whether or not you can view URLs based on who you are, where you're coming from, what group of users you might be in, that type of thing. Excuse me. It will also scan for malware that a web server is attempting to serve out. It may categorize URLs so that you can make decisions as to whether or not to go to that URL, or who might be allowed or who might be denied going to that URL. You can have web application filtering. So that's monitoring HTTP traffic for applications to look for known attacks or malicious behavior. And these can also encrypt and decrypt information flowing between a machine on the internet and the web server. 10.1.6 is check your understanding on the first section on endpoint security. You can do that on your own, and we will move on to access control. We're going to talk about 3A's again here in a moment, but one of the most common things you do is authenticate with a local password. So a server can have a local password, routers and switches can have local passwords, a PC can have local passwords, etc. So what they're showing you here is a router, and it's showing you that we are protecting virtual terminals. In this case, we're requiring the use of Secure Shell. We have a username admin with a quote strong password and that type of thing. So there are different types of local passwords that we have on Cisco iOS devices. I've already talked in pretty good detail about the 3A's of security. They're using an analogy here that in the case of a credit card account, you prove who you are by having possession of a credit card. So one thing I didn't talk about when I teach the Security Plus classes, on the midterm or final, I had a question that said, what are the 3 most common ways to authenticate? And I'll give you a hint. All 3 of your answers should start with something you. So the first one is something you know, like a user ID and password or PIN. Something you have, like an RSA token, or in this case, this analogy, a credit card. And the last one is something you are, which is biometrics, fingerprints, blood vessel patterns in the eyes, etc. So your authentication is, I'm in possession of my credit card. The authorization in this case is not access to something on the network or computer, but it's access to a credit limit. So it's telling you what your credit limit is or what your credit balance is, how much you can actually spend. And then in this case, accounting, instead of being log in, log out records, database changes, that type of thing, is every single transaction you did. What date was it? What was the amount? Who was it to, for example? So that's a pretty good analogy of the 3 A's using a credit card. So going back to authentication, we're going to talk about all 3 A's in different sections here. We can authenticate. In this case, we have a local user password database on the router, and we authenticate against that router and then gain access to a corporate network. Here we have what they're calling server-based authentication, which is we ask the router to authenticate. It's going to ask us for maybe our user ID and password, and instead of the router making the decision as to whether that's available, it's going to pass it off to what they're calling an AAA server. So this would be something like TACX or a Radius server that would actually do the authentication, and then it would send back a message to the router that says, yeah, they're good to go, or no, for whatever reason, bad password, we've blocked that user or disabled that user, that type of thing. So that's local and server-based. Again, once you prove who you are, then you have authorization. And basically, again, the authorization is what are you allowed to do. So this may be a user access control list, or it may be information coming from this AAA server. And then finally, the last A is accounting. In this case, the router is basically sending log entries to the AAA server. These might be login attempts, the date and time, etc. Might log commands that the user is issuing while they're on. There are different levels of logging or accounting that could be done. And then down here, we have 802.1x. This is port-based access control. So basically what happens is we ask the switch to do something, and then the server does the client-based authentication, determine whether or not we have access to do that. So there are different roles. We have a client, and this is a wired or wireless device that is wanting to do something. We have an authenticator, which is going to request information from the client or the end user, and then it's going to verify that information with the server, and then it is going to send back information whether or not this user was authenticated, and then from there, then what access does the client have. 10.2.7 is a check your understanding on the second section, access control. Of course, you can do that on your own. And we will move on to layer 2, security threats. So here they're refreshing our memory as to the OSI model, and then some of the protocols or information that we have. So a lot of times a compromise starts at layer 2. We're going to spend time talking about layer 2 security threats. And once you have compromised layer 2, you might be able to compromise layer 3, which is address information. We may be able to spoof protocols, spoof ports, and at layers 5, 6, and 7, the upper layers, we have lots and lots and lots of protocols that we can attempt to compromise. These compromises could be straight in, like for example, we could hammer the web server and try to break into the web server using HTTP up here directly. Or we can maybe do the initial compromise at layer 2 and then kind of work our way up in an attempt to compromise the web server. So 10.3.2 talks about switch attack categories. We're going to talk about some of these in more detail in section 10.5. But just going through them real quick, we have MAC table attacks. This could be MAC address flooding, or it could be MAC spoofing. MAC flooding is sending frames with many MAC addresses, bogus MAC addresses, in an attempt to use all the memory up on the switch for the MAC address table. If it continually does that, then we can actually break ARP, for example, or the filling of that MAC address table. MAC spoofing is to sniff the network, find a valid MAC address, and then pretend to be the machine with that MAC address in an attempt to gather information. VLAN attacks could be VLAN hopping, which is where you move from one VLAN to try to gain access to another VLAN. Double tagging, you basically put two VLAN tags in a frame. Frame goes to the first switch, it rips off the headers and trailers, and then there's another VLAN tag that may potentially cause that frame to be forwarded yet to another switch. Or you can just attack machines that are on the same VLAN as you. It's a virtual LAN, so it appears like a physical LAN. So you could just attack end devices on there. There are DHCP attacks. DHCP starvation is try to send bogus DHCP requests in an attempt to exhaust all the IP addresses that a DHCP server is configured to give out. There's also DHCP spoofing, where an attacker pretends to be a DHCP server and it gives out IPs. Often, we'll talk about man-in-the-middle attacks several times. This is often the start to a man-in-the-middle attack. We can have ARP attacks. ARP spoofing is the sending of falsified ARP messages in an attempt to intercept data that's intended for another device. ARP poisoning is also the sending of falsified ARP messages, but basically you're trying to associate an attacker's MAC with a valid IP address of another computer, again, so that you can intercept traffic from that device. Address spoofing attacks is the modifying of addresses, either MAC addresses or IP addresses, in frames to do malicious things. And then finally, the last one that's listed is a spanning tree protocol attack. You can send bogus configuration and or topology changes to the network, or you can attempt to spoof being the root bridge to either intercept messages or to cause a denial of service attack. Down here, they're talking about how do we mitigate some of these different types of attacks. So the first one is port security. Uh, that is a way to prevent many of the attacks that do bad things to the MAC address table. Basically, you put those entries in the MAC address table and basically say these are the devices that are on this port, and nobody else can talk. DHCP snooping can go through and watch what's going on and prevent DHCP starvation or DHCP spoofing attacks. We have dynamic ARP inspection, which inspects the ARP process and is going to prevent our ARP attacks. And then we have something called IP source guard that basically prevents us from screwing around with the MAC address and IP address spoofing attacks. So down here they're talking about ways to be secure in general. Always use the secure version. Don't use Telnet, use SSH. If you're using a web server, use HTTPS instead of HTTP. Use scopy instead of rcopy. Use FFTP instead of normal FTP because everything is encrypted. 10.3.4 is a check your understanding on these layer 2 security threats. You can do that on your own, and we'll move on to some of the MAC address table attacks. So here in 10.4.1, they're just refreshing our memory as to how the MAC address table normally looks. So the purpose of the MAC address table is to show what MAC addresses exist on what ports. And some of the activities we've done, we've seen and reinforced that there can actually be multiple MAC addresses. So if we go from a switch to a hub and that hub has 3 machines connected to it, we may potentially have 3 MAC addresses shown for that port. So what kind of malicious things can we do? So one of the first things we talked about is MAC address table flooding. So what happens is we can use a malicious program called MACOV, which is going to go through and generate random source and destination MAC addresses and send those out. And as the switch is trying to record all those quote machines, it's going to fill up the MAC address table. When the MAC address table is full, we may start getting frames, either bogus or not, that are received that we can't find an entry in the ARP table. So those are then going to be flooded out all the ports, creating unnecessary traffic. Okay, so how do we mitigate that? Well, we mentioned before that we can use something called port security. And basically port security is we specify the MACs that are allowed to send on any particular port, and anything else we just ignore. 10.4.4 is a check your understanding on MAC address table attacks. You can do that on your own, and we'll move to the next section, which is on LAN attacks. So we start this out with a video that's going to talk about some of the sections that are going to follow. It is 5 minutes and 41 seconds long, but I'm going to play that here within the lecture.
A VLAN hopping attack is going to enable traffic from one virtual local area network to be seen by another virtual local area network. And this is without the aid of a device such as a router. This is a basic VLAN hopping attack. A threat actor is going to configure a host to act just like a switch. And then using that host, they're going to take advantage of the automatic trunking port feature that's enabled by default on most switch ports. This would be the modes of dynamic auto or dynamic desirable on the switch ports. The threat actor is going to configure the host to spoof those 802.1q signaling and those DTP messages so that the trunk will form between the host and the switch. With a successful trunk established, they're going to be able to send and receive traffic on any virtual local area network, effectively hopping between any VLANs that they want to connect through. With a VLAN double tagging attack, a threat actor is going to embed a hidden 802.1q VLAN tag inside of a frame that already has an 802.1q VLAN tag. What's going to happen here is we're going to have an attacker that's going to double tag a frame. For example, our attacker was going to build a message that's going to communicate from its current VLAN, which is VLAN 10, with a targeted VLAN of VLAN 20. With the attacker currently being on VLAN 10, they're going to build a frame that's going to have an external VLAN header on it of VLAN 10, and then an internal tagged VLAN of VLAN 20. When that message is sent up to the first switch, our first switch is going to see the external outside header of VLAN 10. It's going to strip that off and then send this traffic on its way to any device running in VLAN 10. Well, the switch sees that VLAN 10 is also the native VLAN, so it's going to remove the VLAN 10 header and move it across the trunk link. Now, as that frame moves across the trunk link, the first header of VLAN 10 was removed. And now the internal tag, which is the VLAN 20, that still exists. This second switch is going to receive that frame, it's going to strip off that VLAN 20 header, and then it's going to forward it out any VLAN 20 ports, which includes down to that targeted host. This is effectively allowing our threat actor machine on VLAN 10 to communicate to the target on VLAN 20 using a double tag. Now, VLAN hopping and this whole idea of VLAN double tagging, they can both be prevented by putting in a couple security guidelines. Number one, we should get rid of trunking on any access port that goes to end devices. Also, the whole idea of auto trunking, using things like dynamic desirable and dynamic auto, that should be disabled. We should use manual static trunking as needed. Also, native VLAN should only be used on trunk links, and that native VLAN should never span to a user device. For instance, in this scenario only works when the threat actor is on the same VLAN as the native VLAN between our switches. DHCP is a powerful tool for easy dynamic addressing across our networks, but it can also be a powerful tool for malicious threat actors that want to have some fun with a network. So, quick recap of DHCP. We have DHCP servers that are going to dynamically provide addressing for us. That addressing includes IP addresses, subnet masks, default gateway, DNS servers, and even more with DHCP options to our clients. The typical conversation with DHCP goes back to DORA. Discover, offer, request, acknowledge. Our client's going to send a broadcast message, which is a discover. A server is going to hear that broadcast message and respond with a unicast offer of, this is what I can give ya. Here's some addressing info. The client receives that offer, it's very excited, and it sends out a broadcast of, I accept the offer you sent me. That server finishes it up with a unicast saying, you like the offer, I'm glad. I acknowledge. And then the lease is complete regarding the client taking that addressing info. It sounds easy enough, but now let's bring in an attack. Now it sounds funny saying it, but there's two common types of DHCP attacks. We've got the DHCP starvation attack and DHCP spoofing. With DHCP starvation, the goal of the threat actor is to create a denial of service for your connecting clients. What would happen is the threat actor would gobble up all of the usable DHCP provided addresses. The easiest way to go about this is having a threat actor using a client machine that's cycling through source MAC addresses very quickly, and for each source MAC address, gobbling up an available IP address being given by your DHCP server. When all the addresses are taken from the DHCP server, there's nothing to provide the legitimate clients. On top of that, there's the DHCP spoofing attack. Imagine having a threat actor putting out their own DHCP server on your network. And when your clients use the whole DORA process and they broadcast out for a discover, and then there's the offer, the request, but then your rogue DHCP server finishes the conversation with the client with an acknowledgement providing wrong default gateway info, incorrect DNS servers, as well as even wrong IP addresses for the clients to use. Effectively, your legitimate clients cannot communicate on the network. So we have to prevent this by using safeguards and implementations for security.
Okay, the next 4 sections go back and talk about some of the things that were covered in the video. The first is a VLAN hopping attack. And as the video said, this is a threat actor or a malicious machine advertising through dynamic trunking protocol that it is a trunk, and it will try to intercept VLAN traffic as if this was a valid trunk line. VLAN double tagging. Basically what you do is you construct a frame that has 2 VLAN tags in it. When that goes across, it goes to the first switch, which was in VLAN 10. It pulls off those VLAN tags, and now it has a tag for VLAN 20. So then what's going to happen is that frame is then going to go to switch ports that are in VLAN 20, and in this case we have a particular machine on VLAN 20 that we're trying to attack. So that's double tagging attack. To mitigate this or prevent this, you can disable trunking on all access ports. So access ports, again, are ports that have end user devices. We can disable auto trunking and cause all trunks to be manually configured, and then we can make sure that the native VLAN is only used for trunk links, no end user devices. As far as DHCP, what they're doing is first telling you how DHCP would normally address, how it would function. So what happens is a client boots up, it sends out a DHCP discovery broadcast that basically says, hey, I'm here, here's my MAC address. Does anybody know who I am and or willing to give me an IP address? The server sees that, it sends back an offer that is a unicast. That means it's going directly to this one machine and says, yes, I have an address I will offer you. And then it's going to broadcast and say, hey, I accept that offer. And then it's going to get a unicast back that says, I acknowledge your request to use this IP address. So that's the DHCP 4-way handshake, how it normally works. So the first attack that we are going to talk about is DHCP starvation attack. Basically what this does is send out bogus DHCP discovery for lots and lots of different hosts, and has the server giving out IP addresses to these bogus MAC addresses, or to match up with these bogus MAC addresses, until all the IP addresses are gone. A DHCP spoofing attack basically tries to finish the 4-way handshake and may assign a wrong IP address, may assign a wrong DNS server, may assign a default gateway, either to prevent a denial or either to perform a denial of service attack, or an attempt to capture machines that it shouldn't. So the way this happens is you have a threat actor here that has a machine that's running malicious DHCP server software. So what happens is a client comes on and says, hey, can somebody tell me who I am? And what happens is, the real DHCP server up here may see that, but the bogus one will see it as well, and see that discover request. So what happens is the rogue or bogus DHCP server tries to do an offer and an offer may come from the real DHCP server as well. But the hope is that the client will get the rogue offer first, and it will go through and request the IP address that it got from the rogue DNS server. So here's the request coming back. And then finally, the rogue server acknowledges the request and back, and now the DHCP client has an IP address that was provided by the rogue DHCP server, not the real DHCP server up here. So that is some VLAN attacks and some DHCP attacks. We're now going to have a video that talks about ARP attacks, spanning tree protocol attacks, and Cisco Discovery Protocol reconnaissance attacks. So this video is 6 minutes and 14 seconds long, and I will play it here in line with this lecture.
Address Resolution Protocol is a powerful protocol on our networks that allow our networks to function. With ARP, we're talking about having a known IP address being mapped to an unknown MAC address. And this is being used all the time with our devices on a network. Now, a client can send an unsolicited ARP reply, which is known as a gratuitous ARP. It's really a broadcast that we have a specific IP address that is mapped to a specific MAC address. Now, the problem is when someone sends out a gratuitous ARP as a broadcast, other devices, which should be hosts as well as network switches, are going to store that MAC address and IP address combo in their ARP tables and MAC address tables. This is an issue because a threat actor can send a gratuitous ARP message with spoofed information inside of it. This effectively allows any host to claim to be the owner of any IP address and MAC address combo that they want to. So let's talk about it. Here in our graphic, we've got PC1, PC2, and R1. They all have ARP caches that are up to date and correct. But what's going to happen here is PC2, the threat actor, is going to send out a gratuitous ARP. And that gratuitous ARP is going to claim that 10.0.0.1, the IP address of the router, is reachable by using MAC address all Cs, which is the MAC address of the threat actor. Also, the threat actor PC2 sends out a gratuitous ARP claiming that 10.0.0.11, which is the IP address of PC1, is reachable with MAC address all Cs, which is again the attacker. So what's going to happen here is when PC1 sends data to the 10.0.0.1 IP address, it'll be sending it at layer 2 to the attacker, which is all Cs. When the attacker receives this data, it'll be using it as a man-in-the-middle attack. When the router responds to 10.0.0.11, the router will be responding to the layer 2 target, the MAC address of all Cs, which again is going to be the threat actor. So what it comes down to is exactly this. PC1 will want to send data to 10.0.0.1, and to do so, it'll send it to the MAC address of all Cs, which is PC2. PC2 forwards that data onto the router. The router will send it outbound to where it needs to go. As the router responds back to that 10.0.0.11 IP address, it'll be responding back targeting all Cs, again the MAC address of the threat actor. This is a beautiful man-in-the-middle attack. Spanning tree is a protocol that is on by default on our Cisco switches. Its job is to provide us redundant connections while maintaining loop-free pathways, and it does it great. But the problem is threat actors can utilize spanning tree to actually change the topology of your network infrastructure. Now, the way they would do this is based off of logical, not based off of physical connections, but they would make their host appear as a root bridge. To do this, they would be sending out bridge protocol data units, which are spanning tree layer 2 messages, and these messages will include a priority of something insanely low, such as 0, for example, here in our graphic. By sending out these spanning tree messages saying that their priority is insanely good, the network infrastructure will view that threat actor's host, which is pretending to be a switch, as the root bridge, and they will all find the best way to reach the root bridge, which means they'll be dropping their main connection between each other and connecting through that switch itself. This allows the threat actor machine to pretty much act as a man-in-the-middle style attack and to be able to see all network traffic moving across this network domain. Cisco Discovery Protocol is a Cisco proprietary Layer 2 link discovery protocol. This thing is amazing. It can be used to verify Layer 1 and Layer 2 connectivity. And the cool thing is it's on by default on all Cisco devices. Now, on that same point, it can be insanely scary that it's on by default on all devices because it's used to automatically discover other CDP-enabled devices that are directly connected. This can even be used to auto-configure some of their connections. Now, while CDP is extremely useful in network troubleshooting, our threat actors can use it to easily discover network infrastructure vulnerabilities. For example, the CDP information that's being sent out, it's being sent out periodically and as unencrypted broadcasts. This information that is periodically sent out and sent out in an unencrypted format includes the IP address of the Cisco device. It includes the Cisco Internet Networking Operating System version. It includes the platform and even based off of the capabilities of that model of the device. It even includes VLAN information and more. So here's a graphic that pulled off of a protocol analyzer showing a CDP message and ripping it apart in this unencrypted, unsafe protocol reaching out to our end devices. So how can we stop our end devices from receiving this periodic unencrypted CDP laden full of info of greatness? Well, 2 commands. We have no CDP run. No CDP run is put in the global config mode of your device, and that will turn off CDP everywhere on your Cisco device. Or you want to leave CDP on for those inter-network device connections between Cisco devices, but just off on the user interfaces. That would be the command no CDP enable. That's in interface config mode, and that's what you use on your interfaces connected down to end devices. We also have LLDP, which is Link Layer Discovery Protocol. It's a ventral neutral flavor of CDP. This is also vulnerable to recon attacks. We can turn this off globally in our global configuration mode using the no LLDP run command. As well as if you want to do interface-specific commands, we can use no LLDP transmit and also no LLDP receive, respectively.
Okay, the next 4 sections talk about things that we saw in the video. 10.5.7 starts out by talking about ARP attacks. And if you recall the ARP process when it's working normally, a device broadcasts an ARP request basically saying, hey, I want to talk to the machine that has this IP address. If you're that machine, please send me your MAC address, because at layer 2 we use MAC addresses to communicate. The ARP protocol, however, allows for devices to kind of proactively send out what's referred to as a gratuitous ARP. And basically, all the host on a local area network is going to store that information. So it's kind of a way to do what I would call pre-populating the ARPA table. Now, the problem is the attacker can have some malicious software that is going to send out gratuitous ARPs with bogus information. So down here, what we're seeing is normal operation with fully populated ARP tables on the PC1, PC2, and router 1. So now the malicious behavior is shown here. PC2 claims to be 10.0.0.1. It also claims to be 10.0.0.11, and it basically says, hey, my MAC address, the way you can reach me, is CC. So they're just using shorter MAC addresses to make it easier to represent and talk about. So now what happens is any devices that want to talk to either 0.1 or 0.11, those are going to go to 0.12, which is the threat actor's PC. So they can do a man-in-the-middle attack or just look at information that's not really intended for them. So basically a man-in-the-middle attack is you set up a situation like this where you want to talk to, let's say, 10.0.0.1, and what would happen is instead of going to 0.1, it would go to the malicious PC. The malicious PC could inspect that frame, and then it could turn around and actually send it to 10.0.0.1. So in this case, the router wouldn't know anything is going on. It would think that the information came straight from PC1, but in reality, it went to this quote, man in the middle. Next section talks about address spoofing attack. Basically, this is when a device lies about its MAC address and sends the MAC address of another PC. Now what's going to happen is this MAC address will add BBBBB into FA0/2, but if PC1 actually communicates, it's going to flip it back to the correct port. So to make this spoofing attack work and possibly intercept packets, the PC, in this case PC2, is going to have to continually keep lying about who it is to try to keep bogus information in the switch's MAC address table. 10.5.9 talks about spanning tree protocol attack. Basically, an attacking host, so down here, this device, emulates a switch and attempts to become the root bridge so that traffic either flows to it, possibly stops there doing a denial of service, possibly is intercepted looking for confidential information, for example, or passes through it like a man-in-the-middle attack like we saw with the ARP attack. So this is what our topology should look like. In this case, we're sending out bridge data protocol units saying our priority is 0, which is lower than any other device, including the real root bridge. And what's going to happen is it's going to become the root bridge. So that's a spanning tree protocol attack that we might have to worry about. And then finally, Cisco Discovery Protocol. It is a layer 2 link discovery protocol. It is very handy for discovering the network topology and also troubleshooting network topology or network connectivity issues in a Cisco network. One of the problems is the Cisco Discovery Protocol packets are sent out encrypted, and they have information such as what type of device is it, what OS is it running, what are the capabilities of the OS or the device, what's information about the native VLAN, etc. Information that a hacker could use to do mischievous things. So there's a couple of solutions. The first is to completely turn off CDP by going into global configuration mode and saying no CDP run, and that completely turns it off. Now what happens is we no longer have the nice things about CDP. So a second solution, probably a better solution, is to leave CDP running on the interfaces that you know connect to other network devices. However, on interfaces that go to end or user devices, you can actually go into the interface configuration mode for those ports and say no CDP enable. So that turns off the Cisco Discovery protocol on the ports that are connected to end devices. However, allows it to continue to run on ports that are connected to other devices. So that takes us to 10.5's Check Your Understanding on LAN attacks. You can do that on your own. And that takes us to the module Practice and Quiz. What did I learn in this module? You can read through this to make sure that you understand all the things we talked about in this module. And then 10.6.2 is the module quiz on the entire chapter, LAN Security Concepts. So you can do that on your own. And that finishes up the lecture on Module 10.